All right, so the rest of today, we are going to talk about the energetics of ionic formation. As usual, there is a set of notes that you can use in Schoology, or you can make your own notes. At the end, we'll ask you to do summary and questions. All right, so let's talk about the energy of ionic bonding, right? And so if we think about the formation of sodium chloride, NaCl, we can measure in the lab that the formation of NaCl from sodium and chloride is highly exothermic. It's negative 410 kilojoules per mole. Okay, so in order to get sodium chloride, we need to make Na plus and Cl minus. So that means we need ionization energy for sodium and electron affinity for chlorine. Well, losing electrons, the ionization energy of sodium is 496 kilojoules per mole. Gaining electrons, the electron affinity for chlorine is negative 349. Okay, so if I do the energy calculation there, right, of 496 minus 349, I should get an overall reaction energetic of positive 149, which would be exothermic. But we know that this thing is which would be endothermic. But we know this thing is super exothermic. So that means we've got to be missing something. As you learned in yesterday's POGL, that missing something is lattice energy. Or another way of saying it is, those numbers don't explain why the reaction of sodium, metal, and chlorine gas is to form sodium chloride is so exothermic. So there's got to be a third piece to the puzzle. So what is not counted for is the new attraction that formed between the positive and negative ion. That energy is called lattice energy. So this is the energy required to completely separate a mole of a solid ionic compound into its gaseous ions. So that's kind of interesting because when we think about it in terms of lattice energy, we think of it's the energy that we're getting by putting ions together. But the way that it's measured is based on how much energy it takes to pull ions apart. Okay? The energy associated with these things coming together is governed by Coulomb's law. Now, we learned earlier this year that when we're talking about the force involved by two charges being attracted or repelled from one another, we have a d squared relationship on the bottom. But for energy, the bottom of this is just d. So in this particular case, the energy, or the lattice energy, is governed by the forces, or the charges of the two ions, as well as the distance that they end up apart from one another. So that means lattice energy increases with the charge on the ions. Okay, so if I have a plus one ion and a minus one ion, you're going to have some lattice energy. But if you have a plus 2 and a minus 2, you're going to have a lot more lattice energy. We can see that illustrated over here. For example, here are some plus 2 magnesium oxide. That has a lattice energy of 3795 kilojoules per mole, whereas something where we only have a plus 1 and a minus 1, like lithium fluoride, is about a fourth of that. Okay. It also increases with decreasing sizes of ions. Why would that be? Well, as the ions that are involved in coming together are smaller, that means they can get closer to one another in the crystal lattice. And so as a result of that, you're going to end up with more lattice energy. Why? Because they are closer to one another, and so D is smaller. As D gets smaller, EEL gets bigger. It's an inverse relationship. All right, so lattice energies, again, as I mentioned before, are written as positive. So it's the energy that it requires to break those bonds. So when bonds are formed, they've got to release energy. And so you end up with a negative value for the lattice energy. Okay, so the magnitude of the lattice energy depends upon the size, charge, and arrangement of ions. The sign on the lattice energy depends upon whether we're talking about the bonds coming together and forming, in which case it would be negative, or whether we're talking about pulling the atoms apart, which would mean it's positive or endothermic. All right, so for accounting for all three energies, the ionization energy, the electron affinity, and the lattice energy, we can get a good idea of the energetics involved in such a process. You can think about the Born-Haber process that we have on page 995, or either of the processes that we talked about in the POGL. Right? So energy involved here, again, ionization energy, making the positive ion, electron affinity, making the negative ion, lattice energy, pulling them together. And then, of course, we still do have heat of formation for how do you go about turning a solid into a gas, or a liquid into a gas, or even splitting a diatomic atom into a monatomic atom. Now, in our metal ions, especially in our transition metals, okay, we know from our discussion of ionization energy that losing more than 3 electrons is hard because we get those very, very large jumps in ionization energy. So in order to make an ionic bond, we need the lattice energy to be greater than the third ionization energy. Okay? Otherwise, things just don't work. So the transition metals have d orbital electrons. However, they lose the p and the s first because of the greater energy level. Okay, so which electron does Fe plus 2 lose versus Fe 3 plus? Well, if we look at just the electron configuration for iron, we see that it's argon, 4s2, 3d6. Okay, so the question is Fe2, what is it losing? Well, it just loses those S2, okay? What about Fe3 plus? Well, Fe3 plus is going to lose the 4s2, but it's also going to lose 1 out of the 3d6, which then leaves us with 3d5, okay? So the implications of this is that the transition metals do not follow the octet rule. If you remember me saying the other day, once we get down into that transition metal area in that D block, things get weird. And so the other thing that we can find out too here is copper, silver, and gold can be +1 ions. And the reason for that, again, is because of their strange electron configuration, where by losing 1 electron, you end up with a half-full sublevel, even by losing that 1 electron out of the 4s.